Okay, this is project one for high-speed aerodynamics. We are modeling a CD nozzle with two conditions. One is a shock in the diffuser, and the other one is the shock pushed out of the diffuser. So I'm going to start with the shock in the diffuser. To start, I had to build my geometry, and to do that, I had to figure out my A over A star ratio. So I built a MATLAB script and all my ratios and stuff to figure out how to build my geometry, what dimensions to use, whatnot. Then I went over to Fusion 360 and I built my CD nozzle right here. So I imported this geometry, this CD nozzle. I imported it into Fluent. You just go here, you right click and replace. Oh, it's gonna be replace here because I've already done it, and then replace it. It took me 5 versions, so yeah. Anyway, so then after you import it, you're gonna make sure that it's imported properly, and we're gonna go to our mesh. And for the mesh, I went with a pretty fine mesh. Here, as you can see, we zoom in. It's triangles. It's not super smooth, but like it's pretty small. It gets the job done. So yeah, from here, make sure all the names sections are good. We're good there. So next would be the solutions tab. So coming in here, we want to make sure we're first set up in our density base because we're doing compressible flow. We're above Mach 0.3 because we're getting shocked. So yep, we have compressible flow. So we want to make sure we're density based so that the way density isn't constant throughout, that'll mess everything up. For my model, energy is on, and using Inviscid for the calculation model. All right, so now we want to go down to fluid, our materials, make sure that our fluid, or using air in our CD nozzle, we want to make sure our density is set to ideal gas. It's typically on constant. And you don't want to use incompressible ideal gas because that kind of defeats the purpose. So the rest of that is fine. In our boundary conditions, this is different from a subsonic nozzle because our inlet, we're going with pressure inlet because we're kind of similar to like a reservoir. So like kind of here, the blue section at the beginning is going to have a really high pressure, and then we're going to set a really high pressure gradient. So that way at the outlet, the pressure is lower. And yeah, so I went ahead and used a pressure of 1 E9 pascals. And then I got what my supersonic static pressure should be from that MATLAB script that I did. So yep, made sure everything there was set good. For the outlet to get a shock in the nozzle, you just kind of have to play around with the back pressure and slowly start increasing it. This is what I ended up getting my back pressure as. I started out by calculating what the back pressure should be, and then slowly increase that number. It took me probably about 5 iterations or 5 times going through to figure out what a good number is. Because you still want to make sure that you're getting the shock. You don't want to have the back pressure too high, or else you're not going to get Mach 1 in the throat. Still want to make sure that it's choked. So, all right. For the methods, I left it how it is. So we're using implicit row dash FDS, least squares, cell, and second order upwind controls. I also left that the same. I changed the module residual monitors. I decreased that to 1E -6. I'm just gonna bring that plot up there. And so yeah, before I went through with my calculation, I set up a solution animation, and I set it to watch the Mach number and update every 25 iterations, so that way I can watch the shock form and as it pushed out, to make sure that the shock wasn't pushing out for this part, to make sure that there was a shock forming. So let me show you that right now. So we're going to go down to animations, playback, play on auto repeat. And if you look here in the window, it will play. So this is when it starts. It starts iterating. You can see here in the throat, a shock is formed and pushes out. That's what this red is. So it's a Mach 1.88 right now. Pushes out, and you can see the flow afterwards. So I think it's pretty cool being able to see it. There's a couple times we watch it push out, and if you leave Fluent running after it pushes out, then it crashes. So here's the residuals. You can see it dropped once like the shock kind of balanced out. So it kind of sat in this place, figured out where it's going to be. So let me show you the contours. So it's pretty cool. You can see the density is really high here, and the high pressure, it's really compressed, and as it pushes out, it's less dense right before the shock, and then it kind of balances out for the density. You can see the speed of sound. Let's compute that, display that. Yeah, high speed of sound, lowers right before the shock and increases after the shock. Same thing with the pressure. You can see high pressure here in the reservoir, and then it's going to decrease right behind the shock, and then increase on it's higher on the other side of the shock, just like we learned in class. And then here's the Mach number, like we just saw in the simulation. So I really like how you can see the shock if you zoom in, the kind of how it goes down, the rainbow effect. What I'm calling it right now. So yep, same thing here. Like you see low velocity, and then it increases in the throat, and then super fast right behind the shock, and in front of the shock, it's slow. I think it's pretty cool being able to see it like visually. So same thing with pressure. You're going to get a lower static pressure right behind your shock, and in front of it where it hasn't hit yet, the pressure it's higher than right in this area. So that is a CD nozzle with a shock in the nozzle, or the diffuse section of the nozzle.